Welcome to the Deep Dive. Today, we're diving into some really interesting machine learning research.
Oh, yeah. What have we got?
It's focused on a huge challenge for autonomous vehicles.
Yeah.
How do you make sure they're safe and reliable, out in the real world?
The safety problem. Always critical. Because they can't just be good in simulations, right? They need to handle unexpected stuff.
Exactly. And this paper we're looking at, it tackles that head on. It's about moving beyond the older safety methods.
Right. Things like the pre-programmed fallback maneuvers, or those complex cost functions trying to steer the car away from danger.
Yeah, those fallback layers and cost functions, they offered some protection, sure, but they had real limits.
Definitely limited. They were kind of rigid, weren't they? Like safety nets that couldn't really adapt or learn.
Precisely. Lots of manual tweaking, no real improvement from experience, and often they made the car too cautious.
Which is great for just driving normally in traffic. Plus, defining all those rules, the mapping data, huge annotation cost.
So this paper introduces something called Centaur. It flips the script a bit.
Okay, Centaur, how does it work?
Instead of just relying on those fixed rules, it uses something called test time training, TTT.
Test time training. So it learns while it's operating.
Kind of, yeah. It refines how the already trained system makes decisions, basically during deployment.
Okay, interesting. How does it refine them?
Well, the core idea is minimizing its own uncertainty about what the best action is.
Uncertainty minimization. And they have a specific way to measure that planning uncertainty.
They do. It's actually pretty clever. They call it cluster entropy.
Cluster entropy. Tell me more.
Imagine the car's considering like a whole bunch of possible driving paths.
Right, multiple options.
Instead of just picking the best one, cluster entropy looks at how the scores for these paths are distributed across general directions. Like, should I go sharp, left, slight right, straight ahead?
So it groups similar paths.
Exactly. It clusters them by direction. And looking at the score distribution across these clusters gives it a sense of, well, whether it's confident or torn between different directions.
That sounds much more intuitive than just looking at tiny path differences.
Yeah, it seems so. And the paper shows some pretty impressive results using this.
On benchmarks.
Yeah, on the standard NavTest benchmark, it apparently set a new state-of-the-art score.
Okay, that's significant.
But maybe even more interesting, they created a new benchmark called NavSafe.
NavSafe. Designed to be tougher.
Exactly. Designed specifically to include those tricky, safety-critical situations that might, slip through the cracks on standard tests, curveballs.
That's really important work. We need benchmarks that push the boundaries on safety.
Definitely. And zooming out a bit, this whole approach, it feels like part of a bigger shift, doesn't it?
How so?
Moving away from just deploying a static finished model towards systems that can adapt and get more robust from their real-world experience.
Yeah, embracing that inference time, computation, and adaptation. It's a promising direction for AI in these high-stakes areas.
Okay, so let's really dig into Centaur now. You said it refines an already trained system. What does that actually look like?
Right, so it's not just tweaking the final trajectory output with a rule like some older methods might. No, it goes deeper. It actually makes subtle adjustments to the internal weights of the neural network itself.
Wow. Okay, so it's fine-tuning itself as it drives.
Pretty much. Think of it as continuous background learning. It uses the data it's seeing right then during operation to make these small updates.
And the goal is purely to reduce that uncertainty measure, the cluster entropy.
Exactly. Reduce that feeling of being torn between directions. And what's really neat is it does this unsupervised. It doesn't need new labels saying that was good driving or that was bad.
Okay, but doing network updates on the fly, that sounds computationally heavy. Does it slow things down? Introduce lag?
That's a really critical question, and they address it. They designed it so the gradient calculations, the math needed for the updates, happen asynchronously.
Asynchronously. Meaning
in parallel, but separate from the main decision-making process, the inference step that decides where to steer right now.
Okay. So update calculations happen in the background.
Exactly. This minimizes any extra latency, which is obviously crucial for self-driving. The car decides its immediate move, and simultaneously, it's learning to make future decisions more confidently.
Clever engineering.
Yeah.
Now, you mentioned earlier that just defining planning uncertainty was tricky for older systems. Why was that?
Well, think about the older end-to-end planners. Many of them just outputted a single trajectory, one predicted path.
Right.
Trying to say how uncertain that single line is.
Yeah.
It's not straightforward, is it? There's no distribution to measure.
Yeah, I see that.
But there's been a shift towards what are called trajectory scoring planners, like the Hydra MDP model that Centaur actually builds on top of.
And those work differently.
Yeah, they generate a whole set of possible future paths, sometimes thousands, and then assign a score to each one saying how good it thinks that path is.
Okay, so multiple options with scores.
Exactly. And once you have that, multiple candidates with associated scores or probabilities, it becomes much more feasible to estimate uncertainty. It's kind of analogous to how a classifier gives you probabilities for different classes.
That makes sense. It gives you something to measure the spread across. So, okay, let's walk through this cluster entropy measure again. How do they calculate it?
Right. So the core insight is treating this trajectory scoring like a classification task over this huge vocabulary of possible paths.
Thousands of paths.
Potentially, yeah. But as we said, just calculating entropy over all those individual path scores isn't very useful because many adjacent paths will have almost the same score.
It doesn't tell you about the big picture direction.
Exactly. It wouldn't tell you if the system is fundamentally confused about whether to turn left or go straight. So they have this neat two-step process.
Okay, step one.
First, they sample a smaller, manageable subset of trajectories from the huge vocabulary. Say M100 candidates.
Just 100. How are they picked?
It's not purely random. It's weighted sampling, biased towards trajectories that tend to score well on average, based on some expert guidance or prior data. They want to focus on the plausible options.
Okay, so they have 100 plausible candidates. What's step two?
Step two is direction-based sampling. They select 5 specific anchor trajectories from those 100 candidates.
Anchors.
Yeah, think of them representing the main driving intentions. Sharp left, straight, slight right, sharp right. This follows some prior work. They pick them based on how far left or right the trajectory goes, the lateral offset.
Got it. 5 directional anchors. Now what?
Now they take the 100 sampled candidates and cluster them. Each candidate gets assigned to the nearest anchor trajectory based on like the L2 distance between the paths.
So 5 clusters, 1 for each anchor direction.
Precisely. Then, for each cluster, they sum up the predicted scores of all the trajectories within that cluster. This gives you a single aggregated anchor score for each of the 5 directions.
Ah, I see. So you get a score for sharp leftness, straightness, etc.
Exactly. Then they normalize these 5 anchor scores to create a simple probability distribution over the 5 directions.
Okay.
And the cluster entropy, H, is simply the Shannon entropy calculated on that 5-way probability distribution.
Wow. That's actually quite elegant.
It is, isn't it? It gives a clear, interpretable measure of uncertainty based on the spread of likely directions, not just tiny wiggles in the path. It captures that high-level directional indecision.
And this cluster entropy score is the thing Centaur tries to minimize during test time training.
That's the objective. Make the planner more decisive, less uncertain about the overall direction it should take. So each time it gets new sensor data, it calculates this H, figures out how to reduce it, and nudges its network parameters accordingly.
You also mentioned a gradient buffer in the paper. What was that for?
Ah, yes, the buffer. That's mainly for stability. Instead of applying the calculated parameter update instantly at every single time step.
Which might make it jumpy.
Could do, yeah. So instead, they keep a short history of the calculated updates, the gradients from the last, say, F4 time steps in a buffer.
Okay, a buffer of 4 gradients.
And the actual update applied to the network uses the average of the gradients currently in that buffer.
Ah, smoothing things out.
Exactly. It smooths the learning process, stops the model from overreacting to very brief moments of uncertainty or flipping wildly between directions based on just one frame of data.
Makes sense. And as you said, this averaging uses past calculation, so it doesn't add latency to the current driving decision.
Right. The decision for now happens while the update based on the recent past is calculated and applied in parallel, ready for the next moment.
Okay, let's talk results. You said NavTest performance was state-of-the-art, that 92.6% PDMS score. How does that stack up against, say, just using a simple fallback safety system?
Oh, the difference is stark. That conservative fallback strategy they compared against, it only got 65.3% PDMS.
Wow, huge difference.
Yeah, and Centaur's 92.6% was getting pretty close to the estimated human performance on NavTest, which is around 94.8%.
And crucially, it improved safety metrics too, like time to collision.
Yes, significant improvements in safety metrics like PTC.
So the fallback system I assume it probably did help with some safety subscores, right? But why did it hurt the overall PDMS score so much?
That's the classic problem with those very conservative rule-based systems. They might prevent certain specific failures, sure, but they often do it by being extremely cautious.
Slamming on the brakes, maybe? Or refusing to merge?
Things like that, yeah. Actions that massively hinder the vehicle's ability to actually make progress and drive efficiently. The ego progress metric dropped way down for the fallback system.
So it's safe, but practically unusable in real traffic.
Likely, yeah. That level of over-conservatism often is. Centaur, though, managed to boost safety while maintaining good forward progress. That's the key balance.
Okay, now tell us more about NavSafe, this new benchmark they created. What was the driving force behind it?
Well, the researchers basically realized that existing benchmarks, while good, might be missing certain types of rare but really important failure cases, edge cases.
The things that only happen occasionally but are critical for safety.
Exactly. They wanted a tougher evaluation, something designed specifically to surface these previously hidden failure modes, scenarios where even good planners might still mess up.
How did they actually build it? Where did they find these scenarios?
They were quite systematic. They started with the pre-crash scenario typologies from NHTSA, the U.S. National Highway Traffic Safety Administration.
Oh, using real-world accident data classifications.
Essentially, yes. Those typologies cover a wide range of common pre-crash situations. They then went through video data from the existing NavTest dataset using a mix of automated tools and careful human review and annotation. And they specifically looked for and tagged clips that matched these safety-critical NHTSA categories, aiming to populate NavSafe with concrete examples of where planners might struggle.
So what kind of tricky situations are actually in NavSafe?
It's a really diverse list designed to test specific skills. Things like handling roundabouts, the yellow light rush or wait dilemma, handling exit ramps smoothly, making unprotected left turns across traffic.
Always stressful, even for humans.
Right. Also, entering ramps, dealing with uncommon traffic signs, overtaking involving lane changes, driving in no-lane areas like parking lots.
Parking lots are chaotic.
And bad weather conditions, plus yielding scenarios, like yielding to pedestrians. It allows for a much more fine-grained look at planner capabilities.
It sounds much more comprehensive than just a single overall score. Did they confirm it was actually different from NavTest data?
They did. They used a method called CLIP-based clustering, and it showed that the data points in NavSafe are, statistically speaking, quite far from the sort of average scenarios in the main NavTest distribution. It really does represent more challenging out-of-distribution situations.
Like those unprotected left turns you mentioned, systems often struggle with judging gaps in oncoming traffic, right? That's the kind of thing NavSafe target.
Precisely that kind of nuanced safety-critical interaction.
So how did Centaur and other state-of-the-art planners actually do on NavSafe? Was it a big struggle?
It definitely highlighted the remaining challenges. The results showed a pretty significant gap between current AI performance, even with Centaur, and human-level driving in these specific scenarios.
So room for improvement.
A lot of room.
Yeah.
While Centaur generally performed better than the baseline model it builds on, and also better than another baseline using a different uncertainty measure called semantic entropy. It also showed, along with the other planners, common weaknesses. Things like exit ramps, as you mentioned, and those no-lane areas proved consistently difficult for most systems. NavSafe really puts the challenges into sharp focus.
The paper also mentioned using cluster entropy not just for training, but also to identify potential failures, like predicting when the model might be about to mess up.
Yeah, that's a really important potential application. If the car can recognize it's entering a situation where it's highly uncertain and likely to fail,
it could warn the driver or request a takeover.
Exactly. That kind of self-awareness is crucial for safe deployment. They ran an experiment trying to predict failures specifically, predicting scenarios where the driving score, the PDMS, would be 0.
The total failure.
Right. They compared cluster entropy against other uncertainty metrics like KL divergence and just the raw entropy over all trajectory scores.
And how did cluster entropy do?
It showed the most promise. It had a better true positive rate for detecting these imminent failures compared to the others. Not perfect, but the best indicator among those tested.
And just to confirm, Centaur did get the #1 spot on the official NavTest leaderboard.
That's right. Using the NaviSim v1.1 simulator environment for the official benchmark, it achieved the top mean PDMS score at the time.
Was that with lots of extra tricks, like model ensembling?
Interestingly, no. The paper notes they achieved this without extensive hyperparameter tuning or using ensembles of multiple models, which the previous top entry apparently did rely on.
So a strong result from the core method itself. Looking back at those NavSafe results, were there specific scenarios where Centaur really shone compared to the baseline, or others where it still struggled significantly?
The per-category breakdown on NavSafe is quite revealing. Centaur did show clear improvements over the Hydra MDP baseline and the Hydra SE semantic entropy baseline in many of the tough categories.
Okay, so the cluster entropy TTT was definitely helping in those challenging spots.
It seems so, yes. It demonstrates the value of adapting using this specific uncertainty measure in those difficult moments. But again, the overall gap to human performance was still substantial across nearly all categories.
Areas like exit ramps and no-lane driving remain tough for everyone.
Yeah, those stood out as persistent challenges, indicating where future researcher really needs to focus. Even the best current systems have a way to go on those kinds of complex maneuvers.
Okay, let's place this in a bit more historical context. How does Centaur fit into the evolution of autonomous driving research?
Well, the field started very modular, didn't it? Separate boxes for perception, planning, control.
Right, the classic robotics pipeline.
Exactly. Then came the rise of end-to-end learning, trying to map sensor inputs directly to driving actions using big neural networks.
Driven by deep learning successes.
Right. Huge potential for scalability and strong results in many cases. But the big question became, how do you ensure these complex, often black box end-to-end systems are actually safe and reliable, especially when they encounter something unexpected?
The safety validation challenge.
Precisely. So Centaur's approach, this test time training, it fits into a broader trend we're seeing in ML, which is leveraging computation at inference time to make models more robust or specialized.
Like fine-tuning large language models after their main training.
Kind of analogous, yeah. Applying a similar philosophy to driving. It's moving away from relying solely on static, predefined safety rules and towards more data-driven ways of reducing uncertainty and improving behavior based on live experience.
A more adaptive approach to safety.
Exactly.
Okay, this brings us perfectly to our novel notions segment. Where could this research lead next? What future ideas does it spark?
Well, one really intriguing direction, I think, is exploring closed-loop test time training with direct environmental feedback.
Closed loop. Meaning
the system doesn't just update based on its internal uncertainty, like Centaur does now, but it also directly incorporates feedback from how its actions affect the environment in the very next moments.
So learning from the immediate consequences. How other cars react, or if it had a near miss.
Exactly. Imagine the car avoids a collision or manages a smooth merge. That positive outcome could directly reinforce the policy updates, perhaps modulating the cluster entropy minimization.
So using real-world interaction as a reward signal?
Kind of, yeah. Drawing potentially from online reinforcement learning ideas. The obvious benefit is more direct adaptation to dynamic situations. But the really non-obvious challenging part is ensuring stability.
Right. Could the policy start oscillating wildly if it's constantly self-updating based on immediate feedback?
That's the key research question. How do you ensure convergence and safety? How fast can it adapt without becoming erratic? It's complex.
What's the potential impact if they could solve that?
Potentially huge. Vehicles that genuinely learn and improve their driving skills continuously in real time. Maybe less reliance on massive pre-training data sets covering every single edge case because the car learns to handle novelty better.
What's the probability map look like? Low chance soon.
I'd say low probability in the immediate term because of the stability and safety validation challenges, but maybe a higher probability longer term as online RL and safety techniques mature. Disclaimer. For entertainment purposes only, of course.
Of course. That's a fascinating, almost sci-fi vision, though. What other notions come to mind?
Another promising area could be combining cluster entropy with other types of uncertainty, specifically evidential uncertainty.
Evidential uncertainty, what's that?
So cluster entropy measures uncertainty in the planner's output, the driving direction. Evidential uncertainty, which they actually touch on briefly in the paper's supplementary materials, tries to quantify the uncertainty in the inputs to the planner.
Like how confident is the perception system about where other cars are, or if it correctly identified a sign?
Exactly. It's about the model's confidence in its understanding of the world state, based on the input data.
Okay, so combining uncertainty about the plan with uncertainty about the perception.
Precisely. Think about the different situations that could create. High cluster entropy, uncertain plan, but low evidential uncertainty, confident perception, might mean the planner sees the world clearly, but just doesn't know the best move.
Okay.
Conversely, low cluster entropy, confident plan, but high evidential uncertainty, unconfident perception could be dangerous. The planner thinks it knows what to do, but its understanding of the situation is shaky.
Ah, that sounds like a bad combination.
It could be. So the interesting research question is, can you develop a joint objective? Something that balances minimizing planning uncertainty, cluster entropy, with maybe being more cautious when evidential uncertainty is high.
A more holistic risk assessment.
Yeah. Could it lead to a more nuanced policy? Maybe it encourages exploration when perception is clear but the plan isn't, but triggers caution when perception itself is uncertain.
What's the real-world impact there?
Cars that have a better sense of their own limitations, they'd know when they don't know, essentially. This could lead to much safer behavior in ambiguous or poorly perceived conditions, like fog or complex sensor readings, and potentially increased trust if the car's uncertainty is more transparent.
Probability map for this one.
I'd rate this one medium probability in the next few years. Researchers are already actively exploring how to combine different uncertainty types in end-to-end systems, so integrating planning uncertainty and evidential uncertainty seems like a logical next step. Again, disclaimer applies.
Disclaimer noted. These are definitely thought-provoking extensions. Okay, let's wrap up.
Right. So the key takeaway is Centaur's really innovative use of this cluster entropy idea combined with test time training.
Yeah, a novel way to improve safety and robustness in these end-to-end driving systems.
And the introduction of the NavSafe benchmark is also a major contribution, really pushing researchers to tackle those harder, safety-critical scenarios.
Definitely. It highlights that while we've made huge progress, there's still a noticeable gap to reach truly human-level performance, especially in those tricky situations.
Absolutely. Plenty of important work still to do.
It really makes you think about the future of deploying these complex AI systems, doesn't it? This idea of adaptation and uncertainty quantification seems key.
It does. For anyone wanting to dive deeper, the link to the actual research paper is in the show notes.
Great. It's clear that machine learning and autonomous driving is constantly evolving, and approaches like Centaur give us a fascinating look at how we might get to safer, more adaptable self-driving vehicles on our roads.